CNC Programming for Beginners, a complete guide. Hi everyone! Welcome back to TechTorqueNK. In today's video, we're diving into the basics of CNC programming. Whether you're new to CNC or just looking to brush up on your skills, this guide will walk you through everything you need to know to get started. Let's get into it! Introduction to CNC. What is CNC? CNC stands for Computer Numerical Control. It's a method used in manufacturing to control machine tools with a computer. CNC machines are used for tasks like cutting, drilling, milling, and turning. Examples of CNC machines and parts they can create. CNC, Computer Numerical Control, machines are automated milling devices that make industrial components without direct human assistance. They use coded instructions to cut a piece of raw material, metal, wood, plastic, etc., into a specific shape. Here are examples of different types of CNC machines and the parts they can create. 1. CNC milling machines. Examples: 3-axis CNC milling machine, most common type, can move along the X, Y, and Z axis. 5-axis CNC milling machine can rotate on additional A and B axes, allowing for more complex shapes and angles. Parts created: engine components, e.g., engine blocks, cylinder heads. Aerospace parts, e.g., turbine blades, structural frames. Medical devices, e.g., orthopedic implants, surgical instruments. Automotive parts, e.g., custom wheels, brake rotors. 2. CNC lathes. Examples: horizontal CNC lathe, most common type, rotates the workpiece horizontally. Vertical CNC lathe rotates the workpiece vertically, ideal for large, heavy parts. Parts created: shafts, e.g., transmission shafts, camshafts. Hubs and bushings. Pulleys. Fittings, e.g., threaded rods, couplings. Basics of CNC programming. CNC, Computer Numerical Control, programming is the process of creating a set of instructions that CNC machines use to perform specific operations. These instructions are written in a language called G-code, which directs the machine on how to move and perform tasks. Understanding G-code is essential for anyone involved in CNC machining because it dictates the precision and functionality of the machine's operations. What is G-code? G-code, short for geometric code, is a standardized programming language used to control CNC machines. It consists of a series of commands that instruct the machine on how to move its tools and execute various functions, such as cutting, drilling, or milling. Each command in G-code specifies particular actions, positions, or parameters, making it possible to automate complex machining processes with high accuracy. Structure of G-code. A G-code program is a text file containing a sequence of instructions, each on a separate line known as a block. Each block consists of several words, which are commands or parameters. Here's an example of a typical G-code line. N10G01X50Y25Z5F150. Breaking down this line. N10, line number, optional, used for organization. G01, command for linear interpolation, a straight line move. X50Y25Z5, coordinates specifying the endpoint of the move. F150, feed rate, which controls the speed of the move. Common G-code commands. G00, rapid positioning. Moves the machine tool quickly to a specified location. G01, linear interpolation. Moves the tool in a straight line to a specified coordinate at a controlled feed rate. G02, circular interpolation clockwise. Moves the tool in a circular path in the clockwise direction. G03, circular interpolation counterclockwise. Moves the tool in a circular path in the counterclockwise direction. G04, dwell. Causes the machine to pause for a specified amount of time. G17/G18/G19, plane selection. specifies the plane in which circular interpolation will occur, X, Y, Z, X, Y, Z. M00, program stop, halts the machine until it is manually restarted. M03/M04, spindle on, clockwise/counterclockwise, starts the spindle in the specified direction. M05, spindle stop, stops the spindle. M06, tool change, changes the tool to the specified tool number. M30, program end and reset, ends the program and resets the machine, creating a G-code program. The creation of a G-code program involves several steps. Design. The part to be machined is designed using CAD, computer-aided design, software. This design includes all dimensions and specifications required for the final product. CAM. The CAD file is imported into CAM, computer-aided manufacturing, software, which generates the toolpaths based on the design. CAM software can automatically generate G-code or allow manual programming for custom paths. G-code generation. The toolpaths are converted into G-code, detailing every movement and operation the CNC machine must perform. This code is typically reviewed and edited by a CNC programmer to ensure accuracy and efficiency. Simulation and testing. The G-code is simulated in the CAM software to verify that the toolpaths are correct and that there are no errors. This step helps prevent potential issues during the actual machining process. Machining. The verified G-code is transferred to the CNC machine, which then executes the instructions to produce the part. Importance of G-code. G-code is critical for precision and efficiency in CNC machining. It allows for the automation of complex and repetitive tasks, ensuring consistent quality and reducing the potential for human error. By providing exact instructions, G-code enables CNC machines to produce intricate and precise parts that would be difficult or impossible to create manually. In summary, CNC programming and G-code are fundamental to modern manufacturing, enabling the precise and efficient production of complex parts. Understanding and effectively using G-code is essential for anyone involved in CNC machining, as it directly impacts the quality and accuracy of the final product. Example CNC program. Percent. O1000, program number. G21, set units to millimeters. G17, select XY plane. G90, absolute programming. M06T1, tool change to tool 1. M03S1500, spindle on clockwise at 1500 RPM. G00X0Y0Z5, rapid move to the starting point above the material. G01Z5F200, move down into the material at a feed rate of 200 mm per minute. G01X50Y0F300, linear move to the first corner of the pocket. G01X50Y30, move to the second corner. G01X0Y30, move to the third corner. G01X0Y0, move back to the starting point. G00Z5, rapid move up out of the material. M05, spindle stop. M30, end of program. Percent. Key components of the program. Program start and setup. Percent, program start /end markers. O1000, program number, used to identify the program. G21, set units to millimeters, G20 would set units to inches. G17, select XY plane for circular interpolation. G90, absolute programming mode, coordinates are relative to the origin. Tool change and spindle control. M06T1, tool change command to select tool number 1. M03S1500, start the spindle rotating clockwise at 1500 RPM. Movements. G00X0Y0Z5, rapid move, G00, to the starting position above the material, X0, Y0, Z5. G01Z5F200, linear move, G01, into the material to a depth of 5 mm below the surface at a feed rate of 200 mm per minute. Pocket milling. G01X50Y0F300, move to the first corner of the pocket at a feed rate of 300 mm per minute. G01X50Y30, move to the second corner of the pocket. G01X0Y30, move to the third corner of the pocket. G01X0Y0, return to the starting point of the pocket. Program end. G00Z5, rapid move up out of the material to a safe height, Z5. M05, stop the spindle. M30, end of the program and reset the machine. Percent, program end marker. Detailed explanation. G21, set units to millimeters. This command tells the machine to interpret all measurements in millimeters. G17, select XY plane. This command specifies that movements and interpolations will be made in the XY plane. G90, absolute programming. This sets the machine to use absolute coordinates, meaning all coordinates are based on a fixed origin. M06T1, tool change. This command changes the tool to tool number 1. M03S1500, spindle on clockwise. This starts the spindle rotating clockwise at a speed of 1500 RPM. G00, rapid move. Rapid positioning commands move the machine quickly to the specified coordinates without cutting. G01, linear interpolation. Linear move commands direct the machine to move in a straight line to the specified coordinates while cutting. Feed rate, F200, F300. The feed rate specifies the speed at which the tool should move through the material. M05, spindle stop. This command stops the spindle from rotating. M30, end of program. This marks the end of the program and resets the machine to its initial state. This simple program demonstrates the basic structure and commands of a CNC program, including setup, tool changes, spindle control, movements, and program termination. Understanding these key components is essential for writing and interpreting CNC programs. Key concepts: coordinates and axes, X, Y, and Z axes. Tool paths, paths the cutting tools follow. Feed rate, speed of the cutting tool. Spindle speed, rotational speed of the cutting tool. G codes and M codes. In CNC, computer numerical control, machining, alongside G codes which control the machine's movements and tool operations. M codes play a critical role in managing auxiliary functions and machine behaviors. M codes are used to command specific machine functions such as spindle rotation, coolant activation, tool changes, and program stops. Understanding M codes is crucial for CNC programmers and operators to effectively control and coordinate the machining process. Here's a detailed exploration of M codes and their functions. Functions controlled by M codes. Spindle control. M codes related to spindle control dictate the rotation and direction of the spindle, which holds and drives the cutting tool. M03, spindle on, clockwise. This M code commands the spindle to start rotating clockwise. It's typically followed by a parameter specifying the spindle speed, like S1500 for 1500 RPM. M04, spindle on, counterclockwise, similar to M03, but commands the spindle to rotate counterclockwise. M05, spindle stop. This M code halts the spindle rotation, stopping the cutting action. Tool management. M codes are also used to manage tools, including tool changes and tool length measurements. M06, tool change. CNC machines often have multiple tools in a tool changer. M06 directs the machine to change to a specified tool number, ensuring the correct tool is used for different operations. M41, tool length measurement. In some machines, M41 initiates an automatic tool length measurement cycle, where the machine measures the length of the inserted tool accurately. Program control. M codes control overall program flow and execution, including starting, stopping, and pausing the machining process. M00, program stop. This M code halts the program temporarily, allowing for manual intervention or inspection of the workpiece. It's often used for pausing the program at specific points. M01, optional stop similar to M00. M01 halts the program temporarily but requires operator acknowledgement to resume. M30, program end, marks the end of the program. When the machine encounters M30, it completes all operations and returns to its initial state. Coolant and lubrication control. M codes manage the activation and deactivation of coolant and lubrication systems, crucial for maintaining cutting tool efficiency and workpiece quality. M07, coolant on commands the machine to activate the coolant system, which sprays coolant onto the cutting area to reduce heat and remove chips. M08, flood coolant on, similar to M07. M08 activates a flood coolant system where coolant flows continuously over the cutting area. M09, coolant off, stops the coolant flow, turning off the coolant system. Machine state and auxiliary functions. M codes can also handle various machine-specific functions and states, such as axis clamping and unlocking. M10/M11, axis clamping and unclamping. In some machines, M10 and M11 commands are used to clamp and unclamp axes or fixtures for workpiece positioning and securement. M13, spindle on, clockwise with coolant, combines spindle activation, clockwise with coolant activation, ensuring lubrication and cooling during cutting operations. M30, end of program with rewind, marks the end of the program and may include additional machine-specific actions like returning to a home position or preparing for the next job. Integration with G-codes. G-codes and M-codes work in tandem within CNC programming. While G-codes primarily handle motion and positioning, M-codes manage auxiliary functions and machine states. Together, they form comprehensive instructions that control the entire machining process, from tool movements and cutting operations to machine setup and maintenance. Examples: G00, rapid positioning. G01, linear interpolation. M03, spindle on clockwise. M08, coolant on. CNC program with these codes highlighted and explained. Here's an example of a simplified CNC program that includes various M codes, each highlighted and explained for clarity. This program will demonstrate spindle control, tool management, coolant activation, and program flow commands. Example CNC program. Percent. O1000, program number. G21, set units to millimeters. G17, select XY plane. G90, absolute programming. M06T1, tool change to tool 1. M03S1500, spindle on clockwise at 1500 RPM. G00X0Y0Z5, rapid move to the starting point above the material. G01Z5F200, move down into the material at a feed rate of 200 millimeters per minute. G01X50Y0F300, linear move to the first corner of the pocket. G01X50Y30, move to the second corner. G01X0Y30, move to the third corner. G01X0Y0, move back to the starting point. M08, coolant on. G00Z5, rapid move up out of the material. M05, spindle stop. M09, coolant off. M30, end of program. Percent. Explanation with highlighted M codes. Program start and setup. Percent, program start / end markers. O1000, program number. G21, set units to millimeters. G17, select XY plane. G90, absolute programming mode. Tool change and spindle control. M06T1, tool change. This command instructs the machine to change to tool number 1. M03S1500, spindle on, clockwise, starts the spindle rotating clockwise at 1500 RPM. Movements and cutting. G00X0Y0Z5, rapid move to the starting point above the material. G01Z5F200, linear move into the material at a feed rate of 200 millimeters per minute. G01X50Y0F300, linear move to the first corner of the pocket at a feed rate of 300 millimeters per minute. Coolant activation. M08, coolant on turns on the coolant system, spraying coolant onto the cutting area. Spindle stop and coolant deactivation. M05, spindle stop stops the spindle rotation. M09, coolant off turns off the coolant system. Program end. M30, end of program marks the end of the program and resets the machine to its initial state. Detailed function explanation. Tool change. M06T1 initiates the tool change to tool number 1, ensuring the correct cutting tool is in place for subsequent operations. Spindle on. M03S1500 starts the spindle rotating clockwise at 1500 RPM, essential for cutting and machining operations. Coolant on. M08 activates the coolant system, which sprays coolant onto the cutting area to reduce heat and clear chips, improving tool life and workpiece quality. Spindle stop. M05 halts the spindle rotation, stopping the cutting action to facilitate tool changes or other adjustments. Coolant off. M09 deactivates the coolant system, stopping the flow of coolant after machining operations are completed. End of program. M30 marks the end of the program and prepares the machine for the next task or resets it to its initial state, ensuring operational efficiency. Integration with G-codes. Throughout this program, G-codes like G00, rapid positioning, and G01, linear interpolation, work in conjunction with M-codes to control machine movements, tool operations, and auxiliary functions. Together, they provide comprehensive instructions for CNC machines to execute precise machining operations efficiently. This example illustrates how M-codes are essential for managing auxiliary functions in CNC programming, ensuring optimal machine performance and safety during manufacturing processes. Understanding and correctly implementing M-codes is crucial for CNC programmers and operators to maximize productivity and achieve high-quality machining results. Understanding the coordinate system. CNC, computer numerical control, machines utilize a coordinate system to precisely control the movement of tools in three-dimensional space. This system is fundamental to understanding how CNC machines operate and how they can be programmed to create complex parts. The primary axes in this coordinate system are the X, Y, and Z axes, each representing a different dimension of movement. The coordinate system. The CNC machine's coordinate system is typically a Cartesian coordinate system, which uses three perpendicular axes to define a point in space. These axes are X-axis. This axis runs horizontally, from left to right when facing the machine. Movement along the X-axis changes the position of the tool or workpiece side to side. Y-axis. This axis runs horizontally but perpendicular to the X-axis, from front to back. Movement along the Y-axis changes the position of the tool or workpiece front to back. Z-axis. This axis runs vertically, up and down. Movement along the Z-axis changes the height or depth of the tool relative to the workpiece. Absolute versus incremental positioning. In CNC programming, movements can be defined using either absolute or incremental positioning. Absolute positioning, G90 in absolute positioning mode, all coordinates are specified relative to a fixed origin point, typically the 0 point of the workpiece or the machine's home position. For example, a command to move to X50Y30 will move the tool to coordinates 50, 30 based on the origin. Incremental positioning, G91 in incremental positioning mode, coordinates are specified relative to the current position of the tool. A command to move to X50Y30 will move the tool 50 units to the right and 30 units forward from its current location. Importance of the coordinate system. Understanding and using the coordinate system is crucial for several reasons. Precision. The coordinate system allows for precise control of the tool's position, enabling the creation of intricate and accurate parts. By defining exact coordinates, the CNC machine can move the tool to specific locations with high precision. Consistency. Using a standardized coordinate system ensures consistency across different machines and programs. This consistency is essential for replicating parts accurately and efficiently. Complexity, the ability to move in 3 dimensions, allows CNC machines to create complex geometries that would be difficult or impossible to achieve manually. By controlling the X, Y, and Z movements, CNC machines can perform operations like drilling, milling, cutting, and engraving with high complexity. Automation, the coordinate system facilitates the automation of machining processes. Once a program is written and the coordinates are defined, the CNC machine can execute the operations autonomously, reducing the need for manual intervention and increasing productivity. Additional axes. While the primary axes, X, Y, and Z, are sufficient for many applications, advanced CNC machines may include additional axes to enhance their capabilities. A-axis, rotational axis around the X-axis. B-axis, rotational axis around the Y-axis. C-axis, rotational axis around the Z-axis. These additional axes allow for more complex movements and operations, such as tilting the tool or the workpiece to machine at different angles, enabling the creation of more intricate and detailed parts. Setting up a CNC machine. Setting up a CNC, computer numerical control, machine is a crucial process that involves preparing the machine for operation to ensure precision, efficiency, and safety. This setup involves several key steps: preparing the workspace, setting up the machine, installing the tools and workpiece, and verifying the setup. Step 1. Preparing the workspace. Clean and organize. Ensure the workspace is clean and free of obstructions. Organize tools, materials, and safety equipment for easy access. Safety precautions. Wear appropriate personal protective equipment, PPE, such as safety glasses, gloves, and hearing protection. Make sure emergency stops and safety guards are in place and functional. Step 2. Setting up the CNC machine. Power up. Turn on the CNC machine and its peripherals. Ensure all systems, including the computer and control software, are operational. Home the machine. Use the machine's control panel to home the machine, which moves all axes to their reference positions. This establishes the machine's coordinate system. Step 3. Installing the tools and workpiece. Select and install the tool. Choose the appropriate tool for the operation. Insert the tool into the machine's spindle or tool holder. Secure it tightly to prevent movement during operation. Set tool length offset. Measure the tool length using the machine's tool length offset procedure. This step is critical for ensuring the tool reaches the correct depth during machining. Load the workpiece. Place the workpiece on the machine's work table. Use a vise, clamps, or fixtures to secure it firmly. Ensure the workpiece is flat and stable to avoid vibrations or movements during machining. Step 4. Setting the work coordinate system. Zero the axes. Use the machine's control panel to move the tool to the desired 0-point origin on the workpiece. Typically, this point is the top surface and a corner of the workpiece. Set work coordinates. Enter the work coordinates into the machine's control software. This step aligns the machine's coordinate system with the workpiece, ensuring accurate tool movements. Step 5. Loading and verifying the CNC program. Load the program. Transfer the CNC program, G-code, to the machine's control software. This can be done via USB, network, or directly from a computer. Simulate the program. Run a simulation of the CNC program in the control software. This step helps identify potential errors or collisions and ensures the program will execute correctly. Dry run. Perform a dry run without cutting material to verify the tool paths and movements. Watch for any unexpected behavior or errors. Step 6. Final checks. Coolant and lubrication. Ensure the coolant and lubrication systems are functioning correctly. Fill reservoirs as needed and check for proper flow. Tool and workpiece check. Double-check the tool and workpiece setup. Ensure everything is secure and correctly positioned. Step 7. Running the program. Start the machining process. Begin the machining process by executing the CNC program. Monitor the machine closely for the first few minutes to ensure everything is running smoothly. Adjust as needed. Be prepared to pause the machine and make adjustments if necessary. This might include tweaking the feed rate, spindle speed, or tool position. Writing your first CNC program. Let's write a simple CNC program to make a square. N10, G21, G17, G90, G40, G49, G80. N20, T1, M06. N30, G00, X0, Y0, Z0. N40, G01, Z1, F100. N50, G01, X50. N60, G01, Y50. N70, G01, X0. N80, G01, Y0. N90, G00, Z0. N100, M30. Detailed line-by-line explanation. N10, G21, G17, G90, G40, G49, G80. N10, line number 10. G21, set units to millimeters. G17, select the XY plane for circular interpolation. G90, set to absolute programming mode, where coordinates are specified relative to a fixed origin. G40, cancel tool radius compensation. G49, cancel tool length offset. G80, cancel any active can cycles. This line sets up the initial conditions for the CNC machine, ensuring the correct units, planes, and modes are selected, and that no compensation or cycles are active. N20, T1, M06. N20, line number 20. T1, select tool number 1. M06, tool change command. This line instructs the machine to change to tool number 1. N30, G00, X0, Y0, Z0. N30, line number 30. G00, rapid positioning command. X0, Y0, Z0, move to the coordinates 0, 0, 0. This line moves the tool rapidly to the origin point 0, 0, 0 without engaging in cutting. N40, G01, Z1, F100. N40, line number 40. G01, linear interpolation command used for controlled movement with cutting. Z1, move to Z coordinate -1 mm, 1 mm below the surface of the workpiece. F100, set the feed rate to 100 mm per minute. This line lowers the tool into the material to a depth of 1 mm at a controlled feed rate of 100 mm per minute, starting the cutting process. N50, G01, X50. N50, line number 50. G01, linear interpolation command. X50, move to X coordinate 50 mm while maintaining the same Y and Z coordinates. This line moves the tool horizontally to X equals 50 mm while maintaining the cutting depth Z equals -1 mm. N60, G01, Y50. N60, line number 60. G01, linear interpolation command. Y50, move to Y coordinate 50 mm while maintaining the same X and Z coordinates. This line moves the tool vertically to Y equals 50 mm, continuing the cutting operation. N70, G01, X0. N70, line number 70. G01, linear interpolation command. X0, move back to X coordinate 0 mm while maintaining the same Y and Z coordinates. This line moves the tool back horizontally to X equals 0 mm, maintaining the cutting depth. N80, G01, Y0. N80, line number 80. G01, linear interpolation command. Y0, move back to Y coordinate 0 mm while maintaining the same X and Z coordinates. This line moves the tool back vertically to Y equals 0 mm, effectively returning to the starting point of the cut. N90, G00, Z0. N90, line number 90. G00, rapid positioning command. Z0, move to Z coordinate 0 mm above the workpiece. This line rapidly lifts the tool out of the material to the original Z position, ending the cutting operation. N100, M30. N100, line number 100. M30, End of program command. This command stops the machine, ends the program, and resets the machine to prepare for the next program. This line signifies the end of the program, instructing the machine to stop and reset. Summary. This CNC program performs a simple rectangular cut in the material. It begins by setting the necessary units and modes, then selects the appropriate tool and positions it at the origin. The tool then lowers into the material to start cutting, moves along a rectangular path, x equals 50 mm, y equals 50 mm, and finally lifts out of the material and ends the program. The commands are straightforward, illustrating basic CNC operations such as rapid positioning, linear interpolation, and feed rate control. Running the CNC program. Load the program into the machine's controller. Double-check the setup and ensure everything is secure. Run the program and monitor the machine. The program being loaded and machine is running. Safety tips. Always wear safety goggles and appropriate clothing. Ensure the work area is clean and free of obstructions. Never leave the machine unattended while it's running. Safety starts from the ground up. Wear proper footwear to protect your feet and ensure stability while working with machinery. Common mistakes in troubleshooting. Incorrect tool selection. Choosing the wrong tool can lead to poor surface finish, excessive wear, or even tool breakage. Solution: verify the tool selection before starting the program. Ensure the tool matches the material and the specific operation, e.g., drilling, milling, or cutting. Improper workpiece clamping. If the workpiece is not securely clamped, it can move during machining, leading to inaccuracies and potential damage. Solution: double-check that the workpiece is securely clamped. Use appropriate fixtures, clamps, or vices and confirm they are tight. Incorrect work coordinate system, WCS, setup. Setting the wrong 0 point can result in the tool starting at an incorrect location. Solution: verify the work coordinate system is correctly set. Use a touch probe or manual measurement to ensure the origin matches the program specifications. Troubleshooting techniques. Identifying the problem. Symptom analysis. Observe and document any irregularities such as unusual noises, vibrations, or tool marks on the workpiece. Error codes. Check the machine's control panel for error codes or messages that can provide clues about the issue. Tool inspection. Wear and damage. Inspect tools for signs of wear or damage. Replace or recondition tools as necessary. Tool holder check. Ensure tools are properly seated and secured in their holders. Program verification. Simulation. Run the CNC program simulation in the control software to identify potential issues before actual machining. Dry run. Perform a dry run without cutting to verify tool paths and movements. Thank you for watching. I hope this video has helped you understand the basics of CNC programming. If you enjoyed this video, please give it a thumbs up and subscribe to TechTorqueNK for more content like this. If you have any questions, leave them in the comments below, and I'll be happy to help. Happy machining! Don't forget to hit the bell icon to get notified when we upload new videos.